welcome. Good job finishing test 2. Like I was saying, I haven't made the adjustments yet, but I will. It's just kind of been a busy week with Pi Day and all yesterday. So yesterday was Pi Day. But I figured I'd share my Pi Day joke with you guys as well. Slice of pie is $2.50 in Jamaica and three in the Bahamas. These are the pirates of the Caribbean. Anyways. Okay, so test 2 is done. That's great. Now we're going to start chapter 6, which is on annuities. Okay, so chapter 6 is on annuities. So I want to spend just a little bit of time talking about annuities. We're going to introduce them more thoroughly in section 6.2. Okay, but I kind of want to give you an idea of why we need to learn the skills that we do in 6.1, because we're going to use them later. Okay? And so an annuity is a term that we use for any sort of loan or savings plan or any payment stream that has regular payments. Okay, so think mortgages, car loans, right? Anytime that you have regular equal payments. Okay, and let me just flip to the page that I want here. Because I'm kind of going off script here. So an annuity, oh, I know why it feels so weird there. An annuity, oh, hello. If you have a question, let me know. Otherwise, I'm going to mute everyone. But if you have a question, you should unmute yourself. All right. So an annuity is a series of equal payments at regular intervals. Intervals. Okay, so for example, right, a car loan, a mortgage, but also things like retirement savings, right? And so you put money into it for some amount of time, and then when you retire, right, then you're slowly taking payments out, probably monthly or biweekly or however often you want money, right? And then so for some amount of time, right? And so maybe even a retirement savings. Okay, right. And we have the tools to solve problems like this. We could use just the formulas that we developed earlier, but what we're going to find is that it's going to be quite complicated. It's going to be a lot of work that we don't want to do, right? And so so we have these new formulas that kind of cut our work in, well, more than half. Okay. So what happens is, so we've dealt with compound interest. So annuities will still have compound interest. So annuities will still be using compound interest. Okay. So the the annuities, the interest is going to be compounding at some frequency. We know how to deal with that, right? But the problem is that the payments, right? There's also some payment frequency. Yeah. So maybe I'll say, which means we will be compounding at a frequency, which we denote by F. Okay. So annuities, right, is going to also have some payment frequency. Okay. And so annuities will also have a payment frequency. Yeah. So there's also going to be some payment frequency. Now, the problem becomes, okay, so part of our formula for compound interest was N, right? Instead of time, we talk about the number of compoundings, right? But now we're going to have some number of compoundings as well as some number of payments. And if we look at our formulas, I'm not going to bring it up now because it's jumping ahead too much, but there's only one N, okay? So in annuities, we let N denote the number of payments, Okay. This means that we're going to need to make adjustments to our compoundings, right? Because our compoundings might be weekly and our payments might be monthly. So what we need to do is we need to figure out what the periodic interest rate is, right? Equivalent to the weekly payment or the weekly compoundings, right? But matching the monthly payments. Yeah. So, for example, if interest is compounding weekly, okay, but payments are made monthly, oops. We need to find the effective interest rate, okay, and I'm using that term on purpose because that's what we're going to call it. We need to find, and maybe I'll say the equivalent interest rate, right, to compounding weekly, right, but changing it to monthly. We need to find the equivalent interest rate that is the equivalent, the monthly compounded rate equivalent to the weekly compounded rate. Equivalent to the weekly compounded rates. Oops. Okay. We did something very similar at the very end of chapter 5. Okay, we said, okay, well, if I have 2.5% compounded continuously, what would be the equivalent annually compounded rate? Okay, so we're going to be able to solve this a little bit easier than what we did, but we already know how to solve it, right? It's just not the fastest way, that's all. Okay, now let me flip back here. So let's start with section 6.1, which is called effective and equivalent interest rates. Effective and equivalent interest rates. So we've talked about equivalent rates, and I'm going to show you how to calculate them, of course. But let's talk about the effective rate. Okay. So the effective rate, which we denote by IEFF. So I is the periodic interest rate, right? And EFF is the effective. Okay. Is going to be the annually compounded rate. So it's just a special case where we've made it the annually compounded rate. So the annually compounded rate that produces the same future value as the given nominal rate. Given nominal rate. So what I'm going to do is I'm going to take us to the formula sheet. Notice that we've finished page 1, so that's got to feel good, right? Especially if you're looking at this, there was quite a lot, but once we kind of pick away at it, right, there's only 2 pages only. But so now we're on page 2. Now for annuities, because we're going to spend a lot of time here in annuities, right? We're going to pick away at each of these formulas, but nothing really changes drastically. Okay. I am going to grab, oh, maybe I'm going to grab here, copy. So the first 2 lines, let's call it, right, just have some calculations that we need to be very comfortable with in switching between different compounding rates, right? We have to, eventually we'll have to change our compounding frequency to match the payment frequency, right? And so there are a couple of formulas that we're going to need. But first, let's talk about this one. Okay. So this is the effective interest rate. So the effective rate, which is the annually compounded rate that produces the same future value as the given nominal rate. Okay. And so let's start with this one here. Copy. Although what we're going to find is that this is just a special case of this one. Okay, so this I2 formula, this one, although it's the largest formula, is the one that we're going to be using the most. Okay, so, but I want to just introduce them. Yeah, go across like this. Okay. So let's see here. Maybe I'll use orange. Okay. Because I'm going to grab them. So this one is where I is the periodic interest rate. Periodic interest rate. This is the same as before. Same as always, right? I equals R over F, right? So you know that one, you're comfortable with that one. That's this I here. Okay. F is going to be the compounding frequency. So it's the same F as before. So F is the compounding frequency. Same as always. The rest of the values here are really just ones. 1 plus I to the power of F and then minus 1 is the effective interest rate. Okay. And so let's see here. And the effective rate is the annually compounded rate, okay, that produces the same future value as are compounded at this frequency. So not annually, but something else. Let's see here. I forgot to add one example 193 to the examples, the chapter 6 examples that I posted. So you'll need to jot that down. Luckily it's a little bit smaller. So I'm just going to bring it in here. What is the effective interest rate of an investment which earns 4.8% compounded quarterly? Okay, and so here, what we want to find is, and maybe I'll use orange again, what's the effective interest rate? So that's IEF. R is 0.048, and quarterly means that F is 4. Okay. So the effective interest rate is 1 plus I to the power of F, then minus 1. So we need I, and what I'm going to do and kind of start to do more is just calculate I equals R over F inside the brackets here. Okay, and so this is going to be the same as 1 plus R over F to the power of F minus 1. I'm not going to show this very often, but it's almost my first time doing it. Sometimes I sneak it in, I know, but almost. 0.048 divided by 4 to the power of 4 minus 1. Okay. So I'm going to bring this to the side here. Oh, that was for a different class. Okay. Using my brackets and just making sure that everything is being calculated properly. 1 plus 0.048 divided by 4, making sure that the 4 is only dividing the 0.048, right? Otherwise, it's not doing what I want it to. Then finish off the brackets to the power of 4, then step it down, minus 1. Okay. Okay. Crop this up here. So the effective interest rate is 0.048. Let's go just to 4 decimal places, 9, roughly. Okay. What does this mean? The effective interest rate is really just changing new frequency is 1, right? The annually compounded frequency or the annually compounded rate that's equivalent to 4.8% compounded quarterly. So what's this saying? 4.89% compounded annually will give you the same result as 4.8% compounded quarterly. Okay. So therefore, 4.89% compounded annually is equivalent to 4.8% compounded quarterly. Okay. Equivalent meaning they would produce the same future value, right? So here, right, equivalent means that from the same present value, they would produce the same future value. Right, over the same amount of time, obviously. Okay. So that's what it means to be equivalent, right? You take some amount, some present value, and it would grow to the same future value, right? But the compoundings are different, and that's okay. That's taken into account. Okay. Okay. Moving across on the formula sheet here. This one, I just want to kind of get it out of the way, is a special case of this effective interest rate. And whenever you see an E or an LN, right, these are having to do with continuously compounded rates. They're very rare. And so it's unfortunate that they take up so much room on our formula sheets because we're not really going to use them a ton. Okay, but let's see here. Right, let's just kind of block this off. Right, continuously compounded special cases. Okay. These are very rare. Okay, these rarely happen or rarely used, let's say. Okay, that doesn't mean that I'm not going to make you use them, right? I've introduced them, so of course they're fair game, but in life and in practice, these are not that common. Okay? And so here, let's say this one, oh, you know what? I should copy it before I draw around it. Copy. Now draw around it. Okay. If the original rate, right? So if the original interest rate is compounded continuously, right? It's a special case. If the original rate or original interest rate is compounded continuously, the effective rate is this guy, and purple is this one. Okay. Notice that it just has R, so we don't need to calculate I. Why couldn't we even do that, right? I is R over F. If the frequency is continuous, right, then we can't do anything about that. So the only clarification that we need here is that where R is the nominal rate. Okay. Okay, let's see if I have, let's do example 197. I wonder why I have 198 before 196 and 197. Sorry about that. I'm gonna grab 197. That's weird. Looks like this whole sheet could use some work. But I'm sure you've noticed it gets progressively fancier, right? So here I've broken it up by section, which I didn't do before. I feel like I always add something as I go, but change the order. That's my addition this term. Okay. An investment earns 6.8% continuously compounded interest. What's the effective interest rate? Right. So here, right, I've got R is 0.06, and I want to know what's the effective interest rate. When it's continuously compounded. So it's that special case. So the effective interest rate is e to the R, then minus 1. Now in this case, it's e to the 0.06, then minus 1. To get e, right, it's a special function, so I need to go to the function, and then there's this italicized e in the lower right-hand corner-ish, e to the power of 0.06, then step it down minus 1. Oops, I didn't step it down. There. Bring this in. Okay. So I get, and maybe let's move this here. We get the effective interest rate is roughly 0.0618. What does this mean? An annually compounded rate of 6.18% is equivalent to 6% compounded continuously. So therefore, 6.18% compounded annually is equivalent to 6% compounded continuously. This is the same problem that we solved earlier, right? And so, and this was last week, so it's been a while, right? But on March 8th, we said, okay, 2.5% compounded continuously. That's so your R is 0.025. So then what can we do? We found, using all this activity here, okay, we wanted to find what it was compounded annually. And so what can we do? We can use the formula that we just introduced, right? And we can say, okay, e to the original interest rate, which was 2.5%. So 0.0, oops, to the power of, and not 2, but to the power of, there, 0.025, okay, and then step it down -1. 0.2531512. Oh, what's the CRN number for this course? That is a question indeed. I don't know. I can look it up after class though. It'll be on Class Finder, I think. But yeah, remind me after class. I'll find it. Okay. All right. Let's see here. So, right, we could have just used this formula. We didn't have this formula yet, right? We went through and we were still able to solve this problem, right, using the tools that we had. And so we were not, lost with the tools that we have. It's just going to be a lot easier with the things, with what we are about to learn. Okay, so I wonder if I should we can use, I'll write down what I just talked about. We can use this formula to confirm our answer from the end of chapter 5, from the end of chapter 5. The effective interest rate is e to the 0.025 minus 1 is roughly, and I'm just going to copy it down here, 0.025. Oh, maybe put it here, is roughly 0.025 31512052. That's approximately equal to. Yeah. Which is a lot faster, right? Oh, thank you. There's the CRN in the chat. Nice. Thank you, thank you. I don't know. All right. So these are the effective interest rates. Okay. Now we're going to talk about just plain equivalent rates, right? Which is what we have been doing, but it's been a special case, right? So note, effective rates are the special case where we are changing from some compounding frequency to annually compounded. Our effective rates are the special case where we change from some compounding frequency to annually compounded. What if we want to do something other than annually compounded, right? In that initial example, where I kind of introduced why we're about to work with all these interest rates that we're going to do. Okay, and so here, what if we want some other compounding frequency, some other than f equals 1? What if we want a different compounding frequency? Okay, then what? Equivalent rates, so this is to kind of get us there. Equivalent rates are when two interest rates have the same effective rate, okay? Right, because what are you doing? You're taking your first interest rate, you're making it annually compounded, and then you're taking your second interest rate and you're making it annually compounded, and then you're making sure that those are the same. Okay, so technically, equivalent interest rates. Two interest rates that have the same effective rate. So what I want to do is I want to develop the formula that's on your formula sheet. Now, you're not going to have to do this again. I just want you to see how it works, and then we can just use the formula on the formula sheet, right? So it will be on the formula sheet, so you don't have to worry about it. But here's how we get there. So we're going to have some effective interest rate 1. And I'm going to force it to be equal to some effective interest rate 2. Now I'm using subscripts for group 1 and group 2. Okay. So if I expand this, I get 1 plus I1 to the power of F1 minus 1 is 1 plus I2 to the power of F2 minus 1. Right? Any sort of group 1 and group 2 specific things get a little subscript, but other than that, not so bad. So what I'm going to do is I'm going to be moving from some compounding frequency 1 to some compounding frequency 2. So what I want to do is I want to solve for I2. Okay. So here, solve for I2 from here. We can do that. I can add 1 to both sides. Luckily, these just dissolve then, right? And so here, then I get 1 plus I1 to the power of F1 is equal to 1 plus I2 to the power of F2. Okay. If I'm solving for I2, then I need to get I2 on its own. And the first thing I need to do is I need to take the F2th root of both sides. Okay. Remembering how exponents work, right, and square roots work, what does this become? This becomes, I can write it out like this, the F2th root of 1 plus I1 to the power of F1 is equal to 1 plus I2. But I can rewrite this a little bit cleaner, right? The F2th root is the same as 1 over F2 in the power, which means that you have 1 plus I1 to the power of F1 over F2 is equal to 1 plus I2. Oops, 2. So close. We just need to solve for I2, which I'm going to do by subtracting 1 from both sides, but also I'm going to switch them because I like to have I2, the thing I'm solving for, on the left-hand side. So I2 is 1 plus I1 to the power of F1 divided by F2 and then minus 1. And there, we did it. Okay. So I'm going to use pink here. First, I'm going to copy. And I'm going to use pink because this one is the most important formula. But notice that this is what we just developed, right? 1 plus I1 to the power of F1 over F2 and then -1. We just figured out how to solve that. Okay, so you don't need to solve for it every time or anything. Oops. I'm going to make it nice and big. Okay, because of the formulas, this will be our most popular formula. And I just hear them working down the hall. They're going to come and check in on some water thing. So when they come to my door, I'll just give you guys a break and we'll just pause for a little bit. Okay. But they're not here yet. I never give you guys breaks. How rude. I know. Sorry. It's because by the time I think of it, class is almost over. Go through. All right. So when are we going to use this? Okay. So this is going to be our most, I guess popular is kind of a weird thing, but popular in the sense that it's the one that we're going to be using the most. Okay. And so what we're going to do is we're going to have a scenario, right, where we want to change from some compounding frequency F1 to a compounding frequency F2. Okay. So maybe I'll say where I1 is the periodic interest rate at F1. F1 is the compounding frequency that we're starting with. So the initial compounding frequency. And F2 is the new compounding frequency. Okay. Let's make a note. F2 later is going to match the payment frequency. Okay. Note, later, F2 will be the payment frequency. I only mention this now because this is probably where you're going to look back to in your notes. Okay, and so when you're trying to figure out when to use this formula, right? And so here it's just important that the payment frequency, that's your new frequency. Okay. We use this formula, or we use this formula, sure. When we want to find the periodic interest rate at a new compounding frequency. At a new compounding frequency. I2 at F2. Okay. So let's do an example. Maybe this is why it's So they're kind of in a weird, we didn't do example 196. I guess I'll skip it. I'm doing 198 now. Okay. 196 got lost. That's okay. So an investment earns 5% interest per year, compounded semi-annually. Okay. How much interest should alternative investments, which are compounded quarterly, pay? Okay. So now what we want to do is we want to find, okay, I've got R1 is 0.05 and it's compounded semi-annually. So F1 is 2, right? Semi-annually means twice a year. So how much interest should alternative investments, which are compounded quarterly, pay? So F2 is now 4 times per year, right? And so make sure you use those subscripts, F1 and F2. The initial one is your F1, and then you're moving to F2. Okay. So I2, we want to solve for R2, but in just like before, right, we need to first solve for I2. So I2 is, 1 plus I1 over to the power of F1 divided by F2, then minus 1. 1 plus 0.05 divided by 2. And maybe I'll clarify here just for the first one, R1 over F1. F1 over F2 minus 1. So 1 plus 0.05 divided by 2. And then I always think of it as going from F1 to F2. So twice per year over 4 times per year minus 1. Being careful with your brackets again, 1 plus 0.05 divided by 2, that to the power of 2 divided by 4. Notice how I'm doing that fraction in the power. You want to make sure that it's all in the power. And then minus 1. I'm going to crop this. So I get I2 is 0.0124 if I go to 4 decimal places. Okay. I probably should find R, right? And so notice, so I2 is R2 over F2. Okay. So R2 then must be I2 times F2. So if I multiply this by 2, so this times 2, right? Because quarterly. F2 is 4. There. Then I get the annually compounded rate. So therefore, or let's jot that, oops. R2 is approximately 0.0497. Therefore, 4.97% compounded quarterly is equivalent to, what was it? 5% compounded semi-annually. Nice. Okay. So another special case is if you have a continuously compounded rate, right? So your I1 and F1 is continuously, okay? And so a special case, another special case where F1 is continuously, so for continuously compounded interest, we can convert to a different compounding frequency. We can convert to a different compounding frequency by, and that formula is on your formula sheet. So I'm gonna scroll up here. Whoa, it's far away. By this formula here. Okay. First, I'm gonna copy it, find a color that I haven't used yet, maybe green. Whoa, it's far away. Where R is the continuously compounded rate and F2 is the frequency that you want to convert it to. So where R is the continuously compounded rate, and F2 is the new compounding frequency. Let's see if I have. Okay, let's do example 203. Probably skipping. Yeah, skipping around a little bit. But that's okay. I'm following the formula sheet, that's why, and I think it's not matching. What monthly compounded rate is equivalent to 9.5% compounded continuously? So here we're saying, okay, so F2 is 12, right? And F1 is continuous. And R, let's see here, R is 0.095. So now I have I2 is e to the r over f2, then minus 1. Okay, nothing crazy going on here. It's just a matter of knowing when to use the formulas that you need, right? And so e is 0.095 divided by 12 minus 1, right? But if you've highlighted all the things that you know from the question, then it's just a matter of plugging them in. So let's see here. E to the power of 0.095 divided by 12, making sure that it stays in the power, right? And then step it out, minus 1. See here. So I2 is roughly 0.007948, but maybe, yeah, it's a little bit more decimal places than I usually keep, but because I started with 2 zeros, I bump it out a little bit more. And because I had a 0 here, it just ended it. Okay. This is per month, right? And so again, I need to calculate. So therefore, R2 is I2 times F2. So I need that one times 12. Bring it in. Should have done it. It's the second time I've done that. So R2 is roughly 0.0954, right? Which means what? It means that 9.54% compounded monthly is equivalent to 9.5% compounded continuously. Right? I don't know what's going on over here, but it's been sorting itself out, so I'll ignore it. What's the last thing that we might want to do here? So we've taken any compounding frequency, converted it to a new compounding frequency. We looked at the special case of, okay, if I have a continuously compounded rate and I move to some numerical compounded rate, right, monthly, weekly, whatever. What if I want to move the other way? Right? What if I want to move from some monthly compounded rate, for example, to a continuously compounded rate? Okay. And so the last thing, and maybe I'll use this kind of special case. The last scenario is when we want to go from some compounding frequency and convert it to a continuously compounded rate. When we want to convert from a compounding frequency to a continuously compounded rate, and this is the last case in that formula sheet. And like I said, these ones in the kind of turquoisey blue section, these are all pretty rare. Sorry about the fuzz here. But we need to be aware of them. Okay. And what's my last color going to be? I used orange, green, purple, blue, I guess. Okay. Where R is the continuously compounded rate F1 yeah, F1 is the frequency that we're moving from. Okay. F1 is the compounding frequency to start, right? F2 is going to be continuously, and then the natural log of 1 plus I1, where I1 is the periodic interest rate, right, initially. I1 is the periodic interest rate initially. Yeah. Oops. Yeah. We want to do example 202. Copy. Paste. So an investment earns 5% interest per year, compounded quarterly. Okay. What is the equivalent continuously compounded rate? Okay. So here, let's just say that it's F1 is quarterly, right? So 4. And what we can say is F2 is continuously. R1 is 0.05. Okay. And so what I want to find is R2, but it's just going to be denoted by R. So R is F1, times the natural log of 1 plus I1, which is the same as R equals F1 times the natural log of 1 plus R1 over F1, right? Just calculating I1 inside. So then R is, in this case, 4 times the natural log of 1 plus 0.05 divided by 4. Do this calculation here. So I get 4 times the natural log of 1 plus 0.05 divided by 4. Make sure that fraction's behaving like we want it to. So then I get an R of 0.04969. Okay. So therefore, 5% compounded quarterly is equivalent to 4.969% compounded continuously. Okay. Now I'm almost tempted to, we're supposed to start the next section, but I don't really want to do that because I posted an assignment and a quiz on this stuff. And so I want you to get really good at doing this conversion before we start section 6.2. Didn't realize it would be so quick. But you guys need a rest. You did a test this week. You did it. So what I'm going to do is I'm going to end it there. I know it feels weird for me too. And give you time to work on the assignment that I posted. And there's also a quiz on it, on this stuff, for you to work through for next week. And then we'll start fresh for annuities on Monday. If you have any questions, let me know. Otherwise, I hope you have a wonderful weekend and enjoy these equivalent rates that you get to do. All right, I'm going to stop this recording.